Yesterday evening, I was browsing YouTube, as I often do when I'm just wasting time, and I saw this cool YouTube video about this paper called Tree of Thoughts. It describes a framework for increasing the effectiveness of using large language models to solve problems. So I watched this whole video, which was 13 minutes long or so, and I didn't really understand what was being talked about. I didn't understand what Wes was trying to communicate. I didn't understand the paper. But I did understand that there was probably something really cool here. So I found the paper, the white paper, and I plugged it into one of those chat with PDF bots. And then I talked with the bot for about 2 hours, and I also tried to read through the paper, which was very hard because I don't know how to read these solution formulas. There's a lot of words in here I don't understand because I don't have a background in machine learning. I don't even have a hardcore computer science degree or anything like that. So a lot of this stuff was going over my head. So I really had to chat with the AI bot for quite a bit. But eventually I got it. And it's not as complicated as it appeared to be at first. A lot of people in the comments section on this video were asking to explain it like they were 5 years old. I found a Reddit thread where there were also a lot of comments in the thread asking if this could please be explained as if they were 5 years old, because I guess I'm not the only one who didn't just immediately understand from watching this video how the Tree of Thoughts framework functions. Although I'll say there were a lot of people in this comments section that seemed to immediately understand it. So I was saying to various people on the forum that I simultaneously felt smart because I finally was able to understand something that, in my opinion, to me is complicated, yet also simultaneously felt kind of stupid because there were so many people in the comments section on a YouTube video that just understood it immediately. So I'm going to explain this as if you were 5 years old, the Tree of Thoughts algorithm. So here we go. So there's two papers. There's this more detailed, more refined paper that came out 2 days after this other paper published by one lab. I don't know if there was multiple people at this lab, but here we've got Princeton University and Google DeepMind working together. Isn't that cool? And here we just have a lab from San Jose. Maybe it's just one guy from San Jose. I think that'd be hilarious if one guy from San Jose managed to come up with more or less the same thing 2 days prior. I'm guessing a lot of people were probably discussing this before someone wrote a paper up, so maybe these people aren't the inventors, but these different publication sources, they put out these papers. And what I found is that both of these papers basically talk about the same framework, the same problem-solving approach. The main difference is that it seems like the problem-solving approach in the DeepMind and Princeton paper uses a depth-first approach, which I think, they talk about here. Whereas the approach outlined in this other paper is more of a depth-first approach, which is outlined in this picture right here. So if you don't know what breadth first and depth first means, because, I don't know, you didn't remember from computer science class or you just don't ever take that, that's okay. I'm going to explain it. All right. So I have two examples for you today. On the left-hand side, I have a breadth-first search approach. And on the right-hand side, I have a depth-first approach. So both of these are valid approaches, and you could come up with other approaches that use different traversal algorithms that are not breadth or depth first, like A star or I don't know what else. And that's just assuming you're using a tree. Something I thought about was that you could potentially use a different data structure that's not even a tree, but I don't know what that would look like. But let's get to it. So let's start with the depth-first search approach. And by the way, they talk about it in the abstract. They say, hey, this is all inspired by just the way that people think in general. Same here. They say the same thing in the abstract up here as well. They say, hey, when we think about things, we come up with different solutions, and then we trial them in our mind, and then we go with the one we think is the best. That's what the Tree of Thoughts algorithm does in a nutshell. It lets you have different solutions and then try them out, weigh the pros and cons, and pick the best. And this is as compared to other approaches. So in the one-shot approach, on the left-hand side here, we have an example where we just put a problem and we just come up with a solution. And this is the least successful in all of their benchmarks. Then we have the chain of thought approach where we break our thinking into steps. So we come up with a problem, but rather than saying, hey, please produce the output from the get-go, we say, can you please think through this in a few different steps? And this has a much better chance of success in their benchmarks, and this has also been around for months or whatever, and people have been finding great success with this. There's another method that generates a set of different strategies based on the initial input and then follows through with chain of thought for each one, then compares which outcomes are the most common and says, hey, those are the most common outcomes, that's probably the one that's the best, let's go with that one. And then the one that's proposed in this paper and this paper is the tree of thought, where instead of just generating multiple approaches at the start and then carrying each one through to completion, we generate multiple approaches at the start, and then for each approach we generate multiple approaches, and at any point in time we might say, hey, this approach is not valid, it's too expensive, it doesn't work, it's broken, it's not feasible, whatever. And so we'll actually backtrack and try different approaches until we find one that wins. And so this is basically making a whole bunch of chains of thought from each of the previous thoughts and stopping at intermediary points and going back and trying other solutions before possibly doing longer range backtracking. For example, in this one, in this green box here, can I move this over? So in this example here, we come up with 3 solutions, and then we go with the first one and we say, hey, that worked, but both of those were failures. So let's just backtrack twice, I guess. Maybe it tried some more and they were failures. So then we try this one and we say, well, that was a failure, that was a failure, this was a success, that was a failure, that was a failure, but this was a success, so output, and maybe this one was a failure from the get-go. So here we're showing an example where we're coming up with multiple thoughts at once, carrying them through to completion, stopping if they're invalid or not feasible before even getting to further logic jumps, and we come up with an output. And so finally, okay, that's all in the paper, that was in the video here, but I didn't understand it, maybe you didn't understand it, so here's my example. Let's say that you're on vacation in Hawaii and you want to boil some water. You tell the large language model that you've got an electric kettle on your kitchen counter, you've got an electric stove in your kitchen, and a stovetop, and you've got a propane camping stove in your car's trunk. So we'll do a breadth first approach. We'll just generate some different thoughts that would be the subsequent next steps. So you might say, well, because I've got all these stoves, let's put some water in a pot. Or you might say, well, because I have a kettle, let's just put this water in the kettle. So those are 2 solutions, right? And so far, neither one of them are invalid. So let's carry their next steps out and see what we get. Well, with the water in the pot, we might want to hike up a volcano because we're in Hawaii. Okay, it's not totally invalid yet. Maybe we want to put the pot on the electric stove or in the oven. And then on the other hand, we have, from our kettle, we can just say, well, we turn the kettle on. Okay, so now we're going to pull out our chains from thin air and lower the water in the pot down the volcano until it comes within a few meters of the magma. Okay, technically this is possible. Let's keep going. For our electric stovetop, we're going to turn it on. For our oven, we're going to turn the stove on or the oven on or whatever. For our kettle, well, hey, we already turned it on and the water's boiling, so cool. We could kind of just stop here. But maybe we want to carry all these solutions out to their completions or failures so that we can find all the successful solutions and then compare them based on what we're going for. Like, are we going for quick, the most convenient method? Are we going for a method that can boil the most amount of water? There's different things that we can optimize here for. So let's look at the next steps. Well, okay, yeah, the water's boiling because the magma boiled the water, the stove and the oven boiled the water. There's no next step here. So then we can say, well, hey, what are we optimizing for? We can go back and look at these and we can calculate, hey, are we trying to find the most cool way to boil water, like the most awesome way? Well, then obviously lowering the water over a volcano is the most epic. So in that case, this one would win. Maybe we're trying to cook and we want to add stuff to the water while we're cooking, then it's on the stovetop, it's in the kitchen, the pot doesn't have a lid. This is the best for cooking. Maybe we're trying to optimize for Thanksgiving dinner and the stovetop's full, so we say, you know what? Let's use all of our stuff. Let's use the oven. So this might be good for Thanksgiving. And finally, maybe we just want to make some tea before going to sleep. We don't need to make a whole bunch of hot water. We really just care about getting a few cups of water boiling ASAP with the least amount of cleanup. Then if we're optimizing for convenience, the kettle might win. So this introduces a thought that I was wrestling with quite a bit, which is, do you calculate the score of the heuristic while you're generating the thoughts and thought steps, or do you generate all of the thoughts all at once, then go back over and calculate the cost or the merit or whatever in separate steps? And that's actually up to you. And in the paper here, the authors do say, like, you can decide that for yourself. So based on the problem you're solving, you can either calculate, you could say, hey, hike up a volcano, I'm optimizing for convenience. That's not convenient. And so you might just rule this one out immediately and say, nope. And then, stovetop, you might say, well, actually, I'm afraid of stovetops, so nope. And then, in the oven, you might say, well, actually, my oven's broken, nope. And then you might say, well, I've got this kettle, cool, turn it on, cool, that works. So, that's, if you're evaluating your options while you're generating your thoughts, then you can short circuit and potentially save yourself time and calculations. So that's an advantage of the tree of thoughts framework. If your problem space is small and you're not going to be generating too many thoughts, you could do it all at once, go back and evaluate them and weigh all the options against each other. And then in that situation, you could optimize for whatever you want and compare different solutions. And so there's the whole idea of like local maximum and minimum and global maximum and minimum. You might evaluate a short-term solution and think it's the best, but in reality, if you evaluate all the options, there might be some other option you have not evaluated yet, which could be the best. So for example, if we weren't making all of these all at once and then going back and evaluating them, we might say that, oh, you know what, that wasn't a success, but this one right here, this one was a success, so we stop here. But then if we're optimizing for convenience, then if we stopped here, we never would have done, this one with the kettle. And so we would have been in a local maximum situation where we found a solution to the problem that was the one that we were currently calculating. And it's not the best, because if we looked at the global solution set, we would say, hey, there's actually this one over here, which is faster and better, more convenient, but we didn't calculate it because we stopped at the first solution here. So by going with the breadth first search, we can evaluate lots of different options and then weigh them against each other. So that's an advantage of the breadth first search algorithm. And I noticed that it seems like the authors of the Princeton paper, they seem to be doing a breadth first search in their examples. So in this example here, we'll see that, hey, there's red, like erroneous thoughts all at the way at the bottom of the tree. If they were short-circuiting at the first erroneous thought, then they wouldn't generate subsequent thoughts. So here we can see we probably generated all of them at once, and because this one was a failure, we stopped. But then here for each one, we generate them all at once, and for these two failures, we stop. But for these successes, we generate all of the solutions at once. These two are bad. This one's good. So I think this is an example of a breadth first search. Although the reason why I don't think this is a depth first search example is because in the second thought on the first level, and then in the third thought on the second level, this one here, we generate a successful thought, but then we also have these failure thoughts. Now, if the successful thought was on the right-hand side, assuming the algorithm generates thoughts from left to right, then I would think, oh, that failed, so we generated this third one, and third time was the charm. But if we're going from left to right, then we'd say, oh, well, this one was successful. We also generated these ones and evaluated them and saw that they were failures. So I think that the authors are doing a breadth-first search here. Let me think about that one more time. Let's say that we're evaluating from right to left with depth first. So failure, no. Success, yes. Failure, no. Success, yes. Okay, if we were doing a depth-first search, then yeah, we'd do failure here, success, cool. But if we were doing a depth-first search, why would we continue to generate these two failures if we're evaluating from right to left, we find this one here, and then why would we go back and calculate another approach? And maybe my recollection of the depth-first search computer science algorithm is just outdated, or I've forgotten some things, but I think this is a depth-first search example here. And again, the authors do highlight further down in the paper, hey, we've got two example search algorithms, breadth and depth first. And they do say that there's other ways that we could do it, like A star and whatever MCTS is, and I'm sure there's more, and they want to do that in future work. Okay, cool. So now let's talk about the depth first search, which I found in the paper by Ji. I don't know how to pronounce his name. Whoa. Anyway. What do we got here? Yeah, so depth first search. So tries something, fails, goes back with the memory module. Tries something, succeeds, fails, goes back with the memory module. Tries something, fails, goes back with the memory module. Hey, the max number of tries per child is 2, so let's backtrack again. And that's the big strength of the tree of thought framework, is that you can backtrack not just a single time, but you can actually backtrack multiple times, and this is how we can really construct a tree structure. So then we try, and succeed. So this is a depth-first strategy. And so here's my example with the depth-first approach. So it's the same example. We want to boil some water because we're on vacation in Hawaii. So we're doing depth first, so we're going to go left to right because that's how I think. So we'll say, all right, let's put some water in a pot. Okay, cool. So then what happens? Well, we hike up a volcano. Now, if we're evaluating these solutions as they're generated, we might just say, hey, that's just too prohibitive. Maybe my leg's broken. Maybe I just don't want to hike up a volcano. So we'll stop there and short circuit. And we won't even look at, lowering the water by, metal chain to the magma, which is pretty epic, right? Super, super epic. But no, we're just going to stop there. Short circuit. Nope. Okay, failure. So let's try the next one. Maybe we have a maximum of 3 thoughts per thought step. So this would be a thought step. This would be a thought. So, all right, we put the water in the pot and then we put it on the stovetop. Cool. Let's try praying to the fire gods. Okay, maybe the fire gods will make the water boil. Well, no, the water didn't boil. So, sorry, fire gods. Okay, that didn't work. All right, well then let's try turning the stovetop on. Hooray, the water is boiling. Okay, but maybe you're afraid of stovetops, or maybe the stovetop is broken, and so instead of water is boiling, maybe because your stovetop is broken, maybe the water's not boiling. This is also something the authors talk about in the paper here, which is that because the tree of thoughts framework involves multiple trips to the large language model, during these intermediary steps, you can have side effects and interact with the real world. And so, for example, let's say that the stovetop was broken, right? You could have an intermediary step which goes and checks and sees, hey, is the stovetop actually working? Oh, it's not working. And so we don't have to just rely on our a priori assumptions from the initial input. At any time, we have a programming framework, like literally the whole computer is at our disposal. We can make connections to the internet. We can get input from sensors. And so we could say, hey, the water's not boiling because, I don't know, the stovetop's broken. Maybe we don't know the stovetop's broken, but we somehow determine, hey, the water's not boiling even though it should. So we backtrack and we say, you know what, we're having a max number of 2 thoughts per thought step or whatever, and these both failed. So let's backtrack again. And again, this is the big advantage of the tree of thoughts framework, is that we can backtrack not just once, but we can backtrack as many times as we want until we get all the way back up to the initial thought. Okay, so we backtrack 2 times. This is called long range backtracking or something like that. It's in the paper. If you look up long range in here, they use the term long range several times. And now we'll say, hey, we put in the pot in the electric oven, we turn the oven on, and it's not boiling because we forgot to close the oven door, I guess. So let's backtrack and close the oven door. Okay, and all right, the water's boiling. All right, but you know what? Maybe the oven is also broken. Man, this oven just sucks. So it's not boiling. So because the tree of thought framework allows for a memory module and allows you to backtrack back up the tree to previous steps to rethink other solutions because your solutions that you've tried have failed, we can backtrack from closing the oven door to turning the oven on to putting the pot in the electric oven. And let's just assume that because I was saying that it's 2 thoughts per thought step before you backtrack, let's just assume we try something else and it, besides turning the oven on, and that also fails. So then we've exhausted all the options. Right? So then we would backtrack to the water in the pot. We backtrack here and we say, all right, well, let's try something else. So we'll put the water in the electric kettle. Cool. That works. Turn the electric kettle on. Cool. That works. And the water is boiling. And yeah, it's super convenient. So this is a depth first search. So in this example of the depth first search, I set it up such that it was the worst case, like everything we tried until the last thing failed, and then the last thing succeeded. So that makes the depth first search look pretty bad. But let's assume that the first thing we tried was just putting water in the electric kettle. And we didn't do, any of this because the first thing we tried succeeded. That is the potential advantage of the depth first search. And again, the authors of this other paper, they highlight a depth first search. And so we can kind of see the example I just went over here, where I from left to right kind of tried things that failed until I found one that succeeded. We can see that's kind of what's going on here as well. They tried things that failed until they found something that succeeded. And then again, looking at the other paper, I was saying it's depth first, or rather breadth first. So in these approaches here, here's a cool breadth first problem. So they use this example of this mathematical game because, oh boy, I love playing games with math, where you're given 4 numbers and some mathematical operations or operators. I think you're allowed to use each one a single time, although I'm not sure about that. I could just Google it, but I'm not going to do that. And you have to calculate 24. So they give 4, 9, 10, 13 to the large language model, and I guess they generate 3 different examples or thought steps. And 2 of them failed, but one of them was somehow valid. They took 10 and 4 and they used the subtraction operator and they're left with 6. So then because they used 10 and 4, they're left with 9 and 13, and they also get to use the number they output, which is 6. So that's why they have 9, 13, and 6. So then they try out 9, 13, and 6 with, I guess they can reuse the mathematical operators. So they try subtraction here and it fails. They try 13 and 9 with subtraction, and that's valid, I suppose. I really should look up the rules to this game, because I don't get why this one is invalid. Like, what, 13 minus 6 is 7? Yes, left 7. I don't get why that's invalid, but whatever. And then they generate all the solutions at a depth first level, and eventually they find one that succeeds. So this is an example of a depth first approach. Now, okay, I'm trying to explain it like I'm 5. I hope I kind of did that with this here. In these examples, you would use language models to determine what's going on. The cool thing about the paper by Zhayong is that they use Sudoku as their example. So come on, where is it? Where is the Sudoku? Okay, here we go. So they've got 3x3 Sudoku puzzles, 4x4 Sudoku puzzles, and 5x5 Sudoku puzzles. So as the dimensions of the puzzles increase, the difficulty also increases. And so 3x3, that's like 3 rows, 3 columns. 5x5, that's 5 rows, 5 columns. So those are the dimensions, right? They have zero-shot approach, which is where you just give the input and then expect an output to work. They have one-shot. One-shot. What is one-shot? I forgot what one-shot means. Literally can't remember what one-shot means. Then they have few-shot, where they give it some instructions, and after giving it some examples of how to do it, it tries to solve the problem. And then they have tree of thought. Man, I really wish I remembered what one-shot means, but I'm just not a machine learning guy. I'm just interested in this stuff because I'm a general programmer. And we can see here with the success rate, 1 being 100% and 0 being 0%, that the Sudoku puzzles for the one-shot, the zero-shot only succeeded 4 out of 10 times on the 3x3. Whereas the tree of thought had a 100% out of 10 puzzles. They say that they ran the test on 10 puzzles, and the tree of thought had a 100% success rate. With the 4x4, 90% versus 20%, and then on the 5x5, the zero shot only succeeded 1 in 10 times, whereas the tree of thought succeeded 8 out of 10 times. So as we can see, that is a huge, stark difference in success rate by employing the tree of thought solution. Now, the tree of thought solution is more computationally expensive than the zero shot, because the zero shot is just one single query to the large language model, whereas the tree of thought solution, each one of these bubbles here on this diagram entails one, possibly multiple queries to a large language model. I don't remember exactly where. In the other paper, they say, I think in the results, here it is, yes, in the results section, the authors say that their tree of thought solution had a 74% success rate versus a 7% rate, or it's low. It's much better. We can see here that it's also almost 0% of time the chain of thought succeeds. I guess that's like 7%. Almost 80% of the time the tree of thoughts succeeds. So in situations where you really want to get the right answer, then I think using tree of thoughts is the right move, because even though it's going to be more computationally expensive, maybe that cost pales in comparison to the accuracy of your result. And everyone in AI is always scaremongering. Everyone's saying, oh, it's all bad. AGI is going to kill us. Somewhere in this paper, they say, hey, this is really bad, or it could be really bad. I'm trying to find here it is. So blah, 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 blah. Humans could bring potential danger or harmful uses by facilitating LMs. I mean, basically, they're just saying, hey, we think that this tree of thoughts framework is such an effective abstraction layer to build on top of language models. It amplifies the effectiveness of the large language models so much that, this could really facilitate harmful uses. I mean, we could already do harmful things with large language models, but I guess this is just the authors doing their typical artificial intelligence people thing, which is scaremongering about artificial intelligence, which is perfectly valid, by the way. I'm sure, it might kill us all, Skynet and all that. I think they said at the top of the paper that it was like a 900% logic improvement. Let's see, can I do a text search? No, but if I look at the clickbait header right here, tree of thoughts, GPT-4 reasoning is improved 900%. I don't remember where the 900% comes from, but it seemed realistic. I'm definitely sure this isn't how percentiles work, but where was it? The 74% number? Yeah, that's over 10 times this. So what is that? Over 1,000% better? Maybe that's where the YouTuber Wes came up with the 900% statistic. Cool. Is there anything? Oh, that's right. There was one last thing I wanted to cover, which is that I actually looked at the code. So the authors here, I don't think they linked any code, but the author here, Jie Long actually linked a code repo on GitHub. So I went and read that this morning. What a great use of my time, because I've been very interested in this since last night. And you can essentially just feed it your own Sudoku and it will try to solve it. So I read through all of the code, and I just want to show you two parts of the code. So the first part of the code is the tree of thought framework itself. And there's some errors in here, or like fix me's or whatever. But basically, this is the loop here that generates the tree structure. So we're saying, hey, for the max number of rounds, which I looked in their config, it's like 100. So 100 times, or if it succeeds, then you, where is it? If solution, return solution or something. There's a piece in here. Yeah. If solution found, return solution. So 100 times, because we don't want to query our large language model a million times. That would actually cost us some, dollars. That wouldn't be good. Unless you're the government and you have unlimited money. That's probably why they were talking about the scaremongering stuff in here. But it says, hey, if you should repeat because maybe the prompt was incomplete, like just continue. Find out if the solution succeeded or not. If it didn't succeed, you failed, try again. If the number of tries is too many, get your rollback steps. And those rollback steps are where we go back up the tree and try other solutions. So this is Python code that more or less implements the tree of thought framework. The other piece of code in this repo that I wanted to show you is in, I think it's in actors. Yes, it's the checker. Right, the checker. So rule-based Sudoku state checker. So you feed in a board and, I guess the current board, so the Sudoku puzzle, like the 5x5 grid of words or numbers, whatever Sudoku is, it's numbers. And then there's just some Python code here that doesn't use language models. It just checks to see if the Sudoku solution that's in progress, so the impartial, currently being completed Sudoku solution, it just checks to see if it's valid or not. And, if it's not valid, it spits out, hey, it's not valid. And then if it's not valid, then it might, try a different approach. And if it tries a bunch of approaches and they're all not valid, because maybe it's an impossible Sudoku setup that seems like it should be valid, but it's not working, we can backtrack more. And the authors actually do say somewhere in this paper that, hey, the reason that we were only able to get like an 80% success rate, because I think they say, so they say right here, hey, we only got an 80% success rate, but where was it? There was I don't remember where in the paper it is, but I think it's here. 80%. I don't know. I'm not going to read the whole thing. But basically they say that this number, this 80% metric, would be higher if the checker code here was able to determine that the current board state seems valid, but in reality will never result in a solution. That'd be like if you were walking up a staircase and then the staircase just had a pit that dropped, 100 meters, and you kept going back down one step and then going back up one step, and you kept encountering that, fathomless, bottomless hole, and you just kept saying, well, I better backtrack a step and retry. You're never going to succeed because that staircase has a bottomless pit that you would fall down and die in. So you can have a Sudoku board where it is passing all the rules in this checker, like it's valid, but you'll never actually be able to complete the result because maybe the different grids when in combination of each other just can't actually follow the Sudoku rules and succeed. So the authors, they say, if we had a better checker, that would make this 80% metric higher. And then the other last thing I wanted to say was that the authors in this paper, the one from Google DeepMind and Princeton, they say, where is the section where they talk about the heuristics? They say that, to evaluate these nodes, like I was saying in my original solution, I was saying, well, if you could evaluate for different things, like is it the most cool? Is it the best for cooking? Is it the best for Thanksgiving? Is it the best for saving time and being convenient? Those are all different like metrics or use cases that you can evaluate for. And when you evaluate those are all subjective things. And so you would use maybe a large language model to apply that subjectivity. But in the authors of the other Tree of Thought paper, where they use the Sudoku problem as their problem space, they don't need a large language model to evaluate whether or not a impartial Sudoku solution is invalid or valid or a success and thus is the solution. That's just, as I showed here, it's just a plain old Python program, rule-based Sudoku state checker. So I'm trying to find which one of these papers outlines it more clearly that you have two approaches? You have the language model approach, and you have, yeah, that's the search one. The thought generator, thought decomposition, chain, blah, 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 blah. Okay, maybe it's the other paper. Let's see. There was a section where they were saying, hey, you could use a language model, or you could use rules. Yeah, checker module, blah, blah, blah. Blah, 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 architecture, memory module, controller, checker module. Yeah, here it is. This is the section. So in this section here, this author basically, and I do believe they outlined this in this paper as well. This paper's got, it's more pages, it's more verbose. They say, hey, it can either be rule-based, that's like the Sudoku puzzle, where you literally can just find any Python program on GitHub for Sudoku and just copy paste the rules. Same for chess and checkers and any game with rules, right? They can be enforced strictly like this. And it could be a rule-based checker. Or you could use a deep neural network to contextually evaluate things. And so in the examples I gave here where I was talking about boiling water, this wouldn't use a rules checker. This would use a language model to generate these thoughts. And, how are you going to evaluate using a computer how costly it is to hike up a volcano versus turning an electric water kettle on? A language model is fit for that task. So you would use a language model for that. So, yep, that's basically what I wanted to cover. Basically, how does the tree of thought framework work when approached with the breadth first and the depth first approaches for an ambiguous problem where the heuristic or evaluation method would use a large language model to evaluate the cost or trade-offs of each thought. I wanted to talk about rules-based versus language model-based heuristic evaluation. I wanted to mention that these different publication sources came up with basically the same concept within 2 days of each other, or at least they put the white papers out within 2 days of each other. And then while I was Googling, trying to find this repo, because I had it open on my iPad but not on my computer, I went and found, someone went and last night, I guess I'm not the only one who had a stroke of inspiration, Kai Gomez or whatever, went and, took the diagram out of the DeepMind and Princeton paper, this one right here, and Kai Gomez went and put that here, and they're talking about what they're going to do. I do anticipate that probably within a week we're probably going to see plugins for Tree of Thoughts on LangChain. We're probably going to see complete examples. My biggest question when I was conversing with the AI chatbot that I'd fed the PDF for this paper into, my biggest question was, given an art, like let's say you're trying to create an artificial general intelligence, well then you don't know what question or problem you're going to be faced with. It might be trying to boil water on vacation in Hawaii, or it might be solving a Sudoku puzzle. So, based on the context of the situation, you don't know if you're optimizing for, correctness or speed or coolness. You don't know if you're going to be querying a language model or if you're going to be using a rule-based checker. Another cool thing about the Tree of Thought framework is that because it involves multiple trips to the language model, at each intermediary trip, you can run other code, including other queries to the language model, to stop and say, hey, should I continue even using the Tree of Thoughts framework? Should I switch over to Chain of Thought? Should I just go to Zero Shot? If someone asks, is the sky blue? You might say, hey, let's pretend that instead of I'm on vacation in Hawaii and I want to boil water, is the sky blue? You might just say hey, this is really simple. I don't need complex problem solving skills. Let's just do Zero Shot. And you would come back with a good answer why the sky is blue. Versus a question like this where you would say, you know what, I think I'm going to need to try a lot of different things and be creative. Let's try Tree of Thoughts. Anything else? Nope, it's escaping me. I think I've talked for almost 40 minutes now. I think I've exhausted everything I wanted to Oh, so in the example I gave here, I was saying, hey, we expect the water to boil when you turn on the stovetop, but it's not boiling. So at each of these intermediary checks, we can make network requests to other services, HTTP services, web servers, whatever, and we can read instrument data. We can get camera data from, like Tesla has their cars that have the cameras on them with the self-driving, and the robots with the vision. I think it's Optimus. So like at each of these steps, we can recalibrate with what the real world sensor data shows us, what the real world results of our past actions have resulted in. You can't do that with a zero shot where you just send a query to a language model. When you just send this query to the large language model and expect a single response, you can't perform like intermediary checks. You could say, hey, I'm going to put the pot on the electric stovetop, and then you might wait like 10 minutes before saying like, hey, these didn't work. And so this is much more suited towards the AGI application, the baby AGI or whatever it's called, Auto GPT, all that stuff, because we can actually pause after each thought or thought step, and we can reevaluate what's going on, and then based on if it's succeeding or not, we can backtrack and try other things. So yeah, that's it. I think this is the first time I've even read a white paper for computer science stuff. So took me like 2 hours before I even understood this, and I'm sure I'm still misunderstanding some things. Oh yeah, one more thing I wanted to mention. A little thought I had last night was that the authors gave examples of these trees here. And when I was looking at this diagram, something that really popped up in my head was, it seems like an evolution of complexity in terms of data structures or algorithmic approaches or framework approaches or whatever you want to call it. Well, what if we went even further than this tree here? I mean, this tree here is a two-dimensional drawing. But what if we used a vector database with, 1,532 parameters? Like Pinecone DB. Right? And so what if instead of a two-dimensional, drawing of where each child can have however many children, but we only can backtrack to the parent, what if the thoughts that are generated were put into coordinate space, like 1,500 parameter coordinate space? This is obviously just like a three-dimensional, four-dimensional, I guess, X, Y, Z, and three-dimensional. Anyway, this still illustrates the concept, right? What if, we used this kind of data structure or approach to structure our tree of thoughts? And then, maybe instead of backtracking towards the parent, we could backtrack towards anything within a certain radius or perimeter, whatever, distance of the parent thought. And also the other thought I had was, what if you saved your trees of thought over time for many different inputs, and you created a vector database of where each of these embeddings here represents a thought step, like one of these. Then in the future, like essentially you're caching this tree of thought result, right? So then in the future, you could potentially, if the same question is asked, or maybe like a different question is asked, but one of the subsequent thoughts ends up being similar or the same as a previously saved thought in a thought step for a different problem. I wonder what that would do. Like maybe it would save you some computation time. I mean, I guess theoretically speaking, if you had all of the questions that could ever be asked and all of the situations that could ever happen, and you had all of the thought steps and thoughts for all of them, right? Then you wouldn't even need to really like run any logic for generating thoughts and thought steps. You could just check your previously thoughts. I mean, that's not quite accurate. You would need to generate thoughts and then look and see if you'd already generated them, and then say, oh, I already generated them. What are those results? But I think we're going to see new data structures here besides trees, and I think we're going to see huge advancements in the effectiveness of artificial intelligence based on this tree of thoughts. this tree of thoughts framework. So thank you, Google DeepMind and Princeton and Jai Long. Very cool stuff. It was interesting.